Jianyi Cheng is an assistant professor at the University of Edinburgh, where he uses formal methods to secure heterogeneous systems. He's going to talk to us today about how do we do heterogeneous compartmentalization in CHERI. And in particular, how do we actually use security properties throughout the SoC? Over to you, Jianyi.
Cool, thanks. Hi, everyone. So we all know about, when we talk about CHERI, mostly we think about CPUs. But in today's system, accelerators are everywhere. In particular, in some of systems like machine learning or graph processing, accelerators are gradually becoming the first-class computing components in the system. But this is mostly because they can explore extensive data parallelism to achieve better performance and energy efficiency, right? A lot of companies or startups now is inventing new architectures, try to push the boundary of performance, but they often overlook one key thing, which is security, right? How do we know that we could safely use them in a system without exposing more problem, right? So this talk is mostly looking into this from the CHERI perspective, can we actually extend the CHERI model to support different accelerators? Okay, so it's not just a theoretical problem, so let's break it down to a specific system, right? We have CPU, and it's a traditional system, so CPU access memory through the interconnects. But when we try to add accelerators to the system, it becomes a master on the interconnect, so it can directly access the memory through the DMA. So here's the problem. Accelerator doesn't have robust security measures nowadays. That means memory access could be at risk. So, for example, saying someone is using one of the accelerator in the system running graph processing. So it's decoding videos. So the video data is stored in the shared memory, right? And in the meantime, there is some malicious person, right? Try to use another accelerator and running seemingly harmless application at the same time. And because this accelerator also can directly access the memory, right? So which means it can access anything that is reachable by the accelerator, potentially try to read or even corrupt the video data. So this is not great. Can we actually prevent that, right? Easiest thing to do, of course, let's do something with software. For example, the CapChecker. But this implementation deeply depending on the operating system and has high overhead. It does not scale very well. So this is often a very complicated thing, right? And we all know about CHERI, which is great. Hardware enforced protection. So why don't we just look at hardware, which has always on protection and it cannot be bypassed by software, okay? So, okay, CHERI is great. And let's take a CHERI CPU and put it in the system, right? So here's the issue. When we introduce an accelerator to a CHERI-based system, this channel is not protected by CHERI, okay? Why? Because the accelerator can directly access memory and can basically bypass whatever CPU has. And this is a serious vulnerability. So what do we have today, right? If we look at a cloud-based system or large-scale system, often we have MMUs, and this is called input-output memory management units. So it kind of protects the memory access not going out of the page size, which is 4 kilobytes, right? But still, 4 kilobytes is a specific number, and it's not always efficient when we deal with different applications. For example, network cards, you will receive thousands or millions of small packets, and which means data corruption or buffer overflow could still happen within the same page. Or we could allocate each small packet in a page, and then it's not efficient, right? So it's not precise enough for fine-grained memory safety. Can we do something else? Yeah. In ISCA 2024, people say, how about I'm going to modify existing accelerator architecture to support this kind of hardware-enforced checks to make sure permission checks, bounds checks, well, not hardened in the hardware data path or control path, right? It works well, but it takes a lot of effort for them to developing this hardware architecture. And it's not scalable across different accelerator microarchitecture nowadays, right? A more important thing is that, when you build this kind of new protect accelerator stick into the system, there are two problems. One is you can't guarantee all the accelerators are protected, and this gap still exists. The other thing is, even the accelerator is protected, and they might speak different language of protection policy with other components, right? For example, this paper, the SNPU speak a completely different language than CHERI. So when we put this in the system, definitely there is a gap between the mismatch of the policy. So bad things could happen, right? So we still need a better and a unified solution for the secured accelerator system. So this is the initial attempt looking at extending CHERI to support accelerators. There are two challenges we're looking at. One is granularity. We have RMUs, which is okay, but can we actually do better? Like looking at finer grain, like what CHERI has at object level. In the meantime, can we actually make everything speak CHERI? So we don't have this protection heterogeneity problem. So taking off-shelf CHERI model, and we can get a lot of sound protections already, right? Then another thing is, this is a research project, right? It's impossible to look at all the accelerators and then basically modify all the architectures to make it CHERI-like. So the idea is, can we actually come up with a general solution that allows us to work with existing accelerators, at least wrapping them up to to make them behave like natively supported CHERI. So this is what we have. We propose CapChecker, a hardware framework. It's basically a lightweight add-on architecture that guards memory accesses from accelerator using CHERI capabilities. So this ensures the CPU and accelerator speak the same policy effectively at a system level. The actual implementation looks like this, but more technical details are explained in the paper. So what has changed in this system, right? Let's talk about thread model. So obviously, let's assume the CPU is already protected by CHERI. And then we're looking at a custom accelerator as the first step. So we assume there is no dynamic memory management on the accelerator. But this still covers a lot of accelerator, like data flow, or like systolic array, or like network card applications. And also, we want to focus on architecture design, and we assume all the software components are trustworthy. So let's revisit the CHERI capability model, right? So how does CHERI prevent like out-of-bound access? So we have this bar represents all the reachable address space of the system, and the operating system holds the capability root. So traditional CHERI capability model, like in a system, the root of capability instantiate different CPU tasks from the root, and then the CPU task can instantiate more sub-tasks on the CPU or data buffers. So in this model, when the CPU task 2 try to access the buffer that belongs to the task 1, then capability will block this access. How about accelerators, right? So in this model, we force each accelerator's task to be allocated by the CPU task. It's very similar to how CPU task works, right? But when we allocate memory, we require the CPU task to allocate data buffers. This is because we assume that the accelerator cannot do dynamic memory management. So the CPU becomes the master of allocating the memories. But the accelerator can still access this data buffers because they have a bigger set of address space than the data buffers, right? So for example, task 1 can access buffer B and C without problem. But when accelerator task 1 try to access data buffer D, it will be blocked by the capability because the address bound obviously does not include that buffer. And also any buffer allocates belong to other tasks, right? This is great because it works with existing CHERI capability model, and we do have accelerated tasks constrained by the capability that cannot get out of the box. So they work with existing model without modifying anything on the CPU side, right? So how does this work in the architecture? Right, so we now illustrate how a high overview of the CapChecker hardware design. So the CapChecker holds a repository of the capabilities, and then these are fetched from the CPU side because the data buffers are all allocated by the CPU. So we just fetch the capability from the CPU. These are treated read-only in the repository, so we can't modify any components. So, and then whenever there is a memory access, it will be decoded, and based on the task and the pointer ID, we will be able to identify the capabilities we want to use. We fetch the capability and we decode it, and we check whether the memory access is valid or not. If everything is okay, we just move it past this to the DMA or interconnect, so everything works as normal. If not, we will trigger an exception flag and put this into the repository and then report this to the CPU. Okay? So how do we allocate and deallocate capabilities? So the information we need on the driver is we need a task ID, pointer ID, and capabilities. So first, when we pass these components to the hardware checks whether this tag is valid or not, which is essential for the CHERI capability. And if it's tag 0, we trigger an error. And then we look through the repository to try to find available slots. If not, it will go simply just stop, right? And if there is an empty line, we just allocate the capability. Same for the eviction. We take these 3 components, and we check the tags, and then we look for the target capability in the repository. If does not exist, it triggers error. Otherwise, we just evict that. Okay, simple. So, yeah, so this is a very simple idea. It works, focused on security. We haven't touched microarchitecture, but it's something in the future work, for future work. But we still wanted to see how good they are, right? And the evaluation we applied is basically 2 questions in terms of security and overhead. I think this is mostly what we care about. So the first thing is how secure it is, right? Unfortunately, there is no, I think this is a big problem in the community. There is no security benchmarks for accelerators because they are so different. So in this work, we look at CWE classifications for CPUs, and we do security analysis to see whether this problem still exists in the accelerator world. And simply, if we talk about granularities, so MMU supports page-level protection, and the other custom accelerator can do a little bit fine-grain. But for this microarchitecture, the SNPU paper, they look at task level. But for the CapChecker, we look at the object level. It's basically pointers. So it's the finest grain compared to related work. Oops, sorry. Yeah, that was a mistake. So there is a special case for 761. So we assume that the software driver or software implementation of the components have the same complexity. And MMUs, when we deal with cascaded pointers, then the MMU has to implement additional features to trace the pointers. And this is more complicated, so it's not supported. But in our work, we take off-shelf capability model, which means when a pointer got dereferenced, and we automatically got this feature for free because it's sitting in the CHERI words. For the other 2 vulnerabilities, it really depending on the architecture, the accelerator architecture, to see whether the granularity is visible or not. The worst case for our work, the best case for our work is objective level, of course. The worst case would be still like task level protection, so things will not go beyond the accelerator boundaries. So still, we provide fine-grained protections across the accelerators. But what is the performance overhead, right? This is what industry cares. So we measure the same application running on 4 different targets. We have normal CPU and CHERI CPU, and then normal CPU plus normal accelerator, and then CHERI CPU plus accelerator, and then CHERI CPU plus CapChecker, right? But the key point here is that if we apply CHERI system-wide, the overhead on the accelerator is way smaller than the CPU. And that is because usually accelerators are deeply pipelined and parallelized. CapChecker sits very well in the hardware pipeline, so it does not become the performance bottleneck. So this is really a great thing. And particularly for this case, we have extremely small overhead, but on average, we have like around less than 5% overhead. So in conclusion, so we try to look at compartmentalizations for heterogeneous system by extending CHERI from CPU to accelerators. And we've developed CapChecker that as a fine-grained hardware protections for accelerator and also across the system. So the CapChecker itself as an add-on, hardware add-on, work with any accelerator architectures and is affordable and is scalable. So what do we want to do? Our future work includes like looking at more complicated accelerators like GPUs, which support dynamic memory management. How do we ensure the capability model still holds? And also, we currently focus on the security of the architecture. So one of our directions is looking at whether we could refine the microarchitecture either as a hardware add-on or actually looking native support, native like CHERI-ifying the accelerator automatically. Cool. Thank you.
Thank you, Jianyi. Are there any questions from the audience? Manu.
Good. Thank you. Yeah, thank you for your talk. I was just wondering, you had on one of your slides, you had essentially all the accelerators funneling through one capability checker. I assume that in a normal scenario, you would usually have all these accelerators have their own port on the bus. So I'm wondering like how you envision that and whether the capability checker essentially serializes all those accesses and give you a performance hit.
Right, I think that's an interesting question and it relates to microarchitecture design. So in our prototype, currently we just have a single capability checker to keep track of all the memory access from all the accelerators. But yes, you can break it down to different copies, and I think it's still safe. It just affects area overhead and the latency overhead. Yeah, it's a scalability issue. Yeah, I agree.
So can I ask a related question?
Yeah.
I guess you have a potentially here, obviously with normal CHERI, you sort of name a capability and then go and use it. Mm-hmm. And here, I guess you run the risk that you could have confused deputy, where one accelerator is basically using a capability that was supposed to be for another one.
Right.
Or even, you know, if one I/O device has been allocated a set of capabilities, it might be using it for the wrong purpose.
Right. So I think that's a good point. So it really aligns on how visible the accelerator is. So here we look at different. Oh. Sorry. Yeah. Oh, yeah. Sorry. Yeah. We really rely on the visibility of accelerator granularity. So we did have two different scenarios. One is everything is wrapped in the accelerator, so we can't really tell anything. In this case, it's basically our worst case, but still we can make sure things do not, like the accelerator still stay in the box. If we know more about this through the I/O device, for example, they have separate physical ports, then we probably can do more. This is where we can reach objective level. Yeah.
Okay, thank you. Any other quick questions?
Thanks. How do you see this interacting with the revocation schemes that we've seen earlier in the afternoon?
Sorry, can you say that again?
The capability revocation schemes that we've seen earlier, you now have capabilities sitting in peripherals.
Right.
And so how do you see those being revocated?
I wasn't in the talk earlier, I think. Sorry.
But presumably you looked at things like cornucopia and cornucopia reloaded. So if you do a suite to revoke.
Oh, I see.
I mean, presumably they can just be revoked.
Yeah.
The revoker's going to need to be aware of the capabilities they're in CapChecker.
Right. So we currently just, on this side, I think it was just the dumbest implementation at the moment. I'm not expert in this side, actually. I mean, technically, I'm just 2-year-old security or CHERI guy. So, I can look in, we'll talk about this offline, yeah. Thanks.
Okay, let's thank Jianyi.
Thanks.